Hello, everyone. Welcome to lesson 16 of Calculus 1. So far we've learned how to differentiate quite a few different types of functions. And last lesson, we learned about the chain rule, which is important for taking the derivatives of functions that are combined or composed within one another. However, there are still a few types of functions that we don't know how to find the derivative of. And these tend to be pretty important functions for certain applications. So, for example, we know that we have the function e to the x, right? This is the exponential function. But what you may have learned in high school is that there is an inverse function for this called the natural log, or ln of x. And remember the role that inverse functions play. Let's say that I have a function, not necessarily one of these, and I decide to plug in 3 into it, and I get out 2. What the inverse function tells me is that if I got 2 from this function, that means I would have needed to plug in 3. So you flip the input and output with an inverse function. Now, there's one stipulation for this. To have an inverse function, f needs to be what's called 1-to-1. What that means is, you actually may have heard of this a different way. It needs to pass the horizontal line test. So for example, of something that wouldn't work with this, let's say we have a function maybe like x squared plus 1. Let's say we want to find out where this function is equal to 2. Well, we could say that this x value, maybe this is 1, will make the function be equal to 2. But then it also seems like -1 would do the same thing. So when we were doing the inverse here, f inverse of 2, what do we plug into the function to give us 2? Well, we could say 1 or -1. So the inverse function doesn't know which one of these it wants to spit out. So in order for the inverse function to exist and spit out only one value, f needs to be 1-to-1. So this would not be an example of 1-to-1, but something more along the lines of this would be. And an easy way to tell by a function's graph if it's 1-to-1 is you should be able to draw a horizontal line anywhere, and it should pass through the function at most once. So it shouldn't be able to pass through twice like it does here. This function will not have a well-defined inverse function everywhere, but this one will right here. Anyways, that's kind of a brief review of inverse functions. Now, in addition to this inverse, there are also inverses of other important functions. Like, for example, let's say we have sine of x, then an inverse function of that is going to be arc sine. Now, there are also inverse functions of things like x squared, and we need to limit this to x being greater than or equal to 0, because if we have negatives, then we run into this problem here. Then the inverse is the square root of x. So we also have inverse functions, but we've already seen how to take the derivatives of these type of functions. And while what I'm about to say will apply to these, there are easier ways of computing these inverses. What we're going to do today will focus mostly on these, where it's a bit more difficult to figure out what the derivative of the inverse will be. All right, so this is setting the stage here. So how do we figure out what the derivative of one of these is? And it turns out that it involves the derivative of the original function. So probably the nicest property of inverse functions is that if you compose them with one another, i.e. you plug one into the other, so I have f inverse of x plugged into f, then you can almost imagine these canceling out, and we're just left with whatever the input of the function is, of the inside function. You can almost imagine that this f and f inverse kind of cancel out and just leave you with x here. And it should work the same way, so long as the other way, so long as your domains and ranges are aligned up nicely. So what we're going to do is we're going to use this fact to help us get our derivative. So like I just said, f of f inverse of x is equal to x. Now what I'm going to do is I'm going to differentiate both sides of this equation. And I'm going to assume that the derivative of my inverse will exist, and that the derivative of my regular function exists as well. So I'm going to take the derivative of this side. Now I have one function plugged into another. So we now know how to deal with that since the last lesson. This is where we use the chain rule. So remember what the chain rule says. We first do the derivative of my outside function, which is f. We have f prime, and we plug in the original inside here. Then we multiply by the derivative of the inside. I'm going to say that's df inverse dx right here. Now we don't know what that is yet because that's what we're trying to compute, but whatever it is, it's going to go right here because of the chain rule, because we have the derivative of the outside with the inside plugged in, and then we have the derivative of the inside. Now over here, if we take the derivative of just x, well, the derivative of x is 1. That's a pretty easy derivative to do. But then notice that we have multiplication here, right? So if we want to isolate this derivative of f inverse, which is what we're trying to get, we simply divide this over to the other side. So the derivative of f inverse of x is none other than 1 over f prime of f inverse of x right here. So this is going to be our rule for differentiating inverse functions. All right, now another way that we could view this is by using Leibniz notation. So if y is equal to f of x, then x is going to be f inverse of y. If we write this in terms of the Leibniz notation, we have that dy dx is 1 over dx dy right here. So this is saying the same thing in Leibniz notation, and you can see why this is true. If we were to take the reciprocal of this, we would have dy over dx. That's another perspective to have here. All right, let's start off with an example. Let's suppose that f of x is x cubed plus 2x plus 4. So I want to accomplish a few things with this. I want to find f inverse of 7, and then I want to find f inverse prime of 7 as well. So that's my goal for these two, for this problem. Now finding f inverse of 7, so remember what f inverse is. It tells you the x value that you plug into your function to get this number. So you could almost think of this as the y value. We kind of have it written up here. F inverse of y is x. So the 7 is like our y value. So we have 7 is equal to x cubed plus 2x plus 4. We subtract 4. We have x cubed plus 2x. And this is a cubic equation, so this might be difficult to solve. But one thing I like to check is I see if we have the coefficients of this, so 1 right here and 2 here. If the coefficients ever add up to be the number in question, that means that x is going to equal 1. Because if I plug in 1 here, I only have the coefficients, and those add to be 3. It seems like x is going to be 1 here, and that is going to be f inverse of 7. So what x value do I plug into this to get 7? It's x equals 1. All right, so we found this. Now I want to find f inverse prime, or the derivative of our inverse function at 7. So we're doing the, well, let me write it like this. So we have f inverse prime of 7. Now using my formula here, this is going to be 1 over f prime of f inverse of 7. All right, now we already know what f inverse of 7 is. We just figured it out. It's 1. So this is 1 over f prime of 1. Now this isn't the inverse function. This is derivative of the original function. So the derivative of my original function we can find by just using the power rule. We have 3x squared plus 2 when we use the power rule here. The derivative of that will be 0. This is going to be 1 over 3 times 1 squared plus 2, or 1/5 right here. So if you ever want to know the derivative of the inverse somewhere, you simply take the reciprocal of the derivative at the matching point, not necessarily 7, so not the same point, but the one that f inverse sends 7 to. All right, so there's our first example. Let's compute some derivative, let's find derivatives as functions. So let's say that, I think I mentioned this earlier, let's say that our function is sine of x. And we know that f inverse of x is arc sine of x, or you'll also see it written as inverse sine of x right here. One thing I want to emphasize, and this is a common misconception, despite this being how reciprocals work, it's not how inverses work. So sine negative 1x is not 1 over sine of x. It's representing the inverse function, the function that we plug into sine to get whatever the argument is. So it's not 1 over sine of x. So don't make that mistake if you see this notation. Okay, so we want to find the derivative of arc sine of x, right? So let's see if we can use our formula here to help us out. So the derivative of the inverse function, arc sine of x, is going to be 1 over f prime of f inverse of x. Okay, well, f of x was sine, right? So f prime of x will be cosine, and f inverse of x is arc sine of x. So we can rewrite this here. We can rewrite this as 1 over cosine of arc sine of x. Now, there's nothing really wrong with this answer. This answer is completely right. This is an acceptable derivative for arc sine, but it turns out that there's actually a much nicer form of this that we want to use. In order to get there, we can use trigonometry to help us out. So what I'm going to do is I'm going to call this arc sine of x, I'm going to call that theta. So if theta is arc sine of x, then if I take sine of both sides, I end up with sine of theta is sine of arc sine of x. Now remember what inverse functions do. If one is plugged into the other, then they cancel out and you end up with whatever the input is. This is saying that sine of theta is x. Now I'm going to do something a little strange. I'm going to write this as x over 1. Now why am I going to do this? It's because sine of theta in terms of trigonometry is the opposite side of the triangle divided by the hypotenuse. If I were to draw a triangle, a right triangle, with this angle theta that I'm using, then the opposite side would be proportional to x, and the hypotenuse would be proportional to 1. Now, because this is a right triangle, I can use the Pythagorean theorem to get what my adjacent side should be. You might be wondering, why do I need to know that? We'll see that in a moment. I'm going to call it a for adjacent. A squared plus x squared is 1 squared. So a squared is 1 minus x squared. So a is the square root of 1 minus x squared right here. And we're going to take the positive square root here. All right, so that's what my adjacent side is here. Now let's go to cosine of theta. So that's my goal here actually, is to get cosine of theta, because I called my arc sine theta. Now cosine of theta is the adjacent side of this same triangle with angle theta over the hypotenuse. And the hypotenuse is still 1, but we now know that the adjacent side is root 1 minus x squared. So it turns out the cosine theta is just none other than root 1 minus x squared. So that's exactly what I'm going to write right here. And this is a much nicer form than this one right here. Like, I don't really understand what this function is. It's kind of bizarre, but this is something that I can have a bit more of a grasp on, because Understand square roots and squares and things like that. This is the derivative of arc sine. Now, one thing I want to note is that's rather strange is that the derivative of this inverse trig function has no trigonometry in this form. So it's kind of interesting that you can write this without trigonometry at all, which is kind of interesting. All right, now I want to let you guys know what the other derivatives of inverse trig functions are. It's a mouthful. Well, let me make a little chart here. So the derivative of arc sine we saw to be 1 over root 1 minus x squared. Now, using exactly the same techniques, we could see, for example, that the derivative of arc tangent is 1 over 1 plus x squared. And then the derivative of arc secant of x is going to end up being, let's see, I think it's the absolute value of x over square root of 1 minus x squared right here, if I remember correctly. This one I don't use very often, so I'm a little more shaky on that one. Now, if I want to get the derivatives for the inverse trig functions of the other three, notice that the other three are their co-versions of these. Now, the neat thing about that is that we have the derivative of, say, arc cosine of x will simply be the negative. There should be an equal there. Should be the negative of what it was for its non-co-version. So arc cosine, we have negative 1 over root 1 minus x squared. For arc cotangent, we have negative 1 over 1 plus x squared. And then for arc cosecant, we end up having negative 1 over absolute value of x root 1 minus x squared right here. All right, so these are the derivatives of all the inverse trig functions, and you can find them all in the same way that you found the derivative of arc sine right here. You can just find them all in exactly the same way as we did here. Okay, so there's the derivatives of the inverse trig functions. So now I want to talk about the other function I mentioned in the beginning of this video, e to the x. So if we have e to the x here, then just a minute, I want to make sure that I get these right here. A little worried my arc secant isn't right. Let's see. Oops, yeah, I thought something was off. Yeah, so it turns out that this should be x squared minus 1. This should be x squared minus 1. Sorry about that. You can see it, though. I don't want to spend too much time on that, but you can see it, that it should be x squared minus 1 by doing this process up here only for secant instead of sine. Sorry about that. I got that flipped around. That reveals that your professor forgot the formulas for these, but that's an indicator of how often they show up. So I would say that out among these two are by far the most important ones to know, especially this one. Arctangent is by far the most common inverse trig function you'll stumble upon. Arc sine appears pretty often. I've seen some arc cosines before in practice, but you almost never see these right here. I mean, I'm not saying they will never appear, but they're very uncommon. So it's mostly, I would say the order of importance is first, second, third, and then tied for a distant fourth. So don't worry too much if you don't remember these ones. They don't appear very often. All right. So let's say we have f of x is e to the x. Now I want to know what the derivative of the inverse function is. So f inverse of x is ln of x. I want to know what the derivative of this is. Well, I'm going to use the same procedure that I've used for the other derivatives. So if I want to know the derivative of an inverse function, then that should be 1 over f prime of f inverse of x. Okay, well, let's see here. So f prime, the derivative of the original function, well, it's e to the x, right? So this is one of our favorite derivatives to do because it's its own derivative. So if f of x is e to the x, f prime of x is e to the x as well. This will be 1 over e, but then rather than plugging in just x, I plug in f inverse of x. I plug in natural log. Now, the thing is that I'm plugging natural log into its inverse function. E to the ln of x, those will cancel out because they're inverse functions. So we end up with just 1 over x. So this goes to show you that the derivative of ln of x is simply 1 over x. And interestingly enough, this doesn't have anything to do with e in here. It's just 1 over x. Okay, so that's how we find the derivative of natural log, which is another function you probably encountered pretty often in high school. So let's look at an example here. So let's say y is ln of x squared plus sine of x right here. Let's say I want to know what y prime is. Well, what I'm going to do, so you see I have this x squared plus sine of x plugged into my natural log, so I'm going to have to use the chain rule for this. So my outside function is ln, and the derivative of natural log of x is 1 over x. I'm going to get 1 over, but then rather than x, I'm going to put in the original inside here. Then by the chain rule, I need to multiply this by the derivative of the inside. I end up with 2x, oops, that's not sine of x, it should be cosine of x right here. So my derivative ends up being 2x plus cosine of x, or x squared plus sine of x. There we go. There was a derivative involving a logarithm. And in general, if we have y being natural log of any function, then y prime will be the derivative of the inside divided by the original function. And this is going to be a fact we're going to use here in just a few examples. All right, next one. Here we have y is ln of the square root of x squared plus 1. Okay, now for this one, we could do the same thing that we did last time. So we could use the chain rule, first with natural log, then with the square root, and then finally with the innermost layer of x squared plus 1. But there's actually an easier way to do this. Remember that the square root is the 1/2 power. Now, if we have a power of something inside of a log, that can turn into the coefficient of the front of the log. This 1/2 can move to the front, and we have ln of x squared plus 1. But notice we haven't done any calculus yet, we've just used log rules. And I emphasize, whenever you can use log rules, it's an excellent idea to do so. It typically simplifies things greatly. Because now, when I want to do y prime, I'm going to have the 1/2 here because it's a constant. And then I have the derivative of ln of something. So we just saw how to do that. I have on my bottom my original thing that was plugged into log. And on the top, I have the derivative of what's in here, which is 2x. And these twos can cancel, actually. So we have x over x squared plus 1 here as our derivative. So this is a lot easier than having to do a triple chain rule. So if you ever see something raised to a power inside your log, simplify it first before using the chain rule. And while the chain rule is useful, it can be kind of confusing to use if we have too many layers. Okay, let's move on to another example. Let's say that y is equal to, I have this all written down here, e to the x squared times the square root of x to the 4th plus x squared plus 1, all divided by cosine squared of x times x cubed plus x squared plus x plus 1 right here. And let's say I wanted to know the derivative of this. Okay, well, this is the lesson on inverse derivatives, right? Or the derivatives of inverse functions. But I don't really see any inverse functions in here. Well, I guess we have a square root, but we already knew how to deal with that. Instead, this looks like something we could do with the quotient rule. But the problem with using the quotient rule here is that this would get really messy, because we have both a nasty denominator and a nasty numerator here. Using the quotient rule on this would involve a lot of chain rule and also a lot of product rule as well. So that might not be the best way to go here. What I'm going to do instead is I'm going to use a technique called logarithmic differentiation. I always have trouble spelling differentiation. I always have to sound it out. I'm going to use logarithmic differentiation here. What I do is instead of taking the derivative right off the bat, I do the log of both sides. So I do ln of y is ln of this monstrosity. 4th x squared and 1, and the cosine and the polynomial. Okay, now why did I do that? It almost seemed like I made everything worse. Well, like I was saying earlier, log rules are there to help us. And we have a bunch of multiplication and division inside our logarithm. This means that we could use log rules to split it up. So for example, I have these two things multiplied up here. Multiplication inside logs turns into addition of logs on the outside. So our numerator will turn into this, and then we subtract, and then we have our bottom here. So we have ln of cosine squared of x minus ln of all of this polynomial. So division is subtraction, so we're subtracting the log of both of these here. Okay. And then even after that, I could do a little more cleaning up. I have ln of e to the something. So that will just yield x squared. And then we saw what happened in a previous example with a square root. This can be gotten rid of, and we can simply replace it with a 1/2. Same thing with the square on the cosine, but there's not much we could do with this one. We're kind of stuck with that. Now I'm going to do the derivative of both sides. Now, I said that the derivative of log of something, if we have log of something, I guess here I called it f of x. If I do the derivative of that, I have 1 over the original thing, and then its derivative on top. So if I do the derivative to all of this, I'm going to have y prime over y, because I'm doing the derivative of log of something. So it's 1 over that something times its derivative. Then I'm also doing the derivative of everything over here. So the derivative of x squared will be 2x. The derivative of this log will be 1/2. And then I put my original thing on the bottom, and then the derivative on top. All right, so there's the derivative of this right here. Then I have the derivative of -2 ln of cosine. So I have -2, my cosine goes down here, and then I multiply by the derivative of cosine, which is negative sine. But these could cancel out and make everything positive. And then finally, I have the derivative of this right here. And then I put the derivative of the inside on top. All right, now you might think we're done here because we did do the derivative, but remember, I was interested in what y prime is, but I actually have y prime over y. So our final answer here is going to be y prime is y times all of this stuff, which I'm going to represent as a squiggle. So I don't want to have to waste your time and write all of that again here. So all I did was I just simply multiplied the y up here times all of this. And that's going to be my derivative. Y prime will be y times all this. Another way we could write that is we could rewrite y in its original form. We have e to the x squared root x to the fourth plus x squared plus 1. And then we have cosine squared x cubed plus x squared plus x plus 1. And then we have that. I guess I'll write it just for the heck of it. 2x cubed plus x plus 2. This is tangent. And then this, I don't think I can do anything nice with. Ooh, there we go. So there is our solution. And as long as that took, so that did take a little bit, although a lot of it was just writing, it would have taken a lot longer to do the quotient rule and all of the necessary chain and product rules involved with this. So if you ever have a complicated looking fraction like this that you need to take the derivative of, logarithmic differentiation is a useful tool for doing that. All right, I want to go over 2 more examples here. Okay, so our next example looks very innocent at first. So our next example here is x to the x, and I want to know what y prime is. All right, well, we already know how to do the derivative of something like x squared, right? For example, x squared, we bring the power down, lower the power by 1, and we have this. So if we did the same with x to the x, well, we would bring the x down, and then we would lower the power by 1. But it's actually kind of funny. If I multiply x to the x minus 1 by another x, which is x to the first power, I end up with x to the x again. So that's kind of interesting. But on the other hand, if we try to differentiate something like 2 to the x, then this will be ln of 2 times 2 to the x. And if we use the same reasoning here, then we have ln of x times x to the x. So using one reasoning with our power rule, we get this. But in using the other reasoning with exponential rules, we end up getting this. So which one actually is it? Well, it turns out that we can't use either of these rules for this function because both of these assume that either the exponent is a constant or the base is a constant. One of them needs to be constant for either the power rule or the exponent rule to work. But that's not the case for this. We have a variable in both the base and the exponent. So how do we deal with this? We're going to use logarithmic differentiation. So I'm going to take the natural log of both sides. And the nice thing about this is that I have a power inside a log. So this power can move to the front, giving me x ln of x. Okay, now I don't know how to differentiate this, but I do know how to differentiate this using what we learned today along with the product rule. So I'm going to do the derivative of both sides now. Anytime I have ln of y, the derivative of that will be y prime over y, just like we had for the previous problem here. Now on this side, I'm going to use the product rule. So I'm going to take the derivative of x, which is 1, and then leave the natural log alone. Then I'm going to leave the x alone and take the derivative of ln of x, and we saw earlier today, that was 1 over x. So when we simplify this, because these can cancel here, and the 1 goes away, we have ln of x plus 1 as our result here. But this isn't what the derivative is. It's not just ln of x plus 1. We need to remember to multiply back in the y. It's easy to forget that. So y prime is y times ln of x plus 1. But what was our y originally, so we can get everything in terms of x? It's x to the x. So it turns out that neither of these answers ended up being correct. It's actually x to the x times ln of x plus 1. Interestingly enough, though, if you distribute the x to the x, then we have ln of x times x to the x here, and then we have x to the x here. It turns out that the derivative is actually the sum of both of these incorrect answers. So I think that's kind of interesting how it's the sum of two things that were wrong. You just add them together, and then it ends up being correct. But anyways, if you ever see a function with a variable raised to a power that also has a variable, logarithmic differentiation is the way to go. All right, now we've learned enough derivative rules to where we could take the derivative of pretty much any function that we wrote down, that we've seen in high school, and any combination of those, meaning we could add, subtract, multiply, divide, we can plug numbers into each other, or plug functions into one another, we can square them, we can involve trig functions, inverse functions, whatever we want. So pretty much any function that's differentiable that we that we've seen in high school, we can now do the derivative of. So I want to do a challenge problem to kind of tie all this together. So let's say that y is arctangent of ln of x raised to the ln of x power. So I want to find the derivative of this. Now, I can assure you, well, I don't know. Maybe there's some weird application out there that uses a function like this, but nothing that I've ever heard of or anything close to this. This is just differentiating this to test our skills. Okay, so we're definitely going to need to use the chain rule here. So the arctangent is our outside function. Now, among all of the inverse trig functions, the one I would recommend you know the derivative of, or be most likely to know the derivative of, is arctan of x. This is 1 over 1 plus x squared. For those of you who ever take calculus 2, this is a very important fact that we use very often in that class. The derivative of arctangent is 1 over 1 plus x squared. So if I do the derivative of my outside function here, I'm going to have 1 over 1 plus, and then I'm going to have ln of x to the ln of x, and then that will be squared here. Okay. Now we could do some things with exponents to tighten that up a bit, but then we need to multiply by the derivative of the inside. So we need to do the derivative of ln of x raised to the ln of x here. So we need to figure out what that is going to be. All right, so I'm going to kind of do this one on the side and then stick it in here as my answer. So this is going to come off to the side here. So let's say that, well, we already used y. Let's say that f of x is ln of x to the ln of x. Now, one thing to note here, if this ln of x were attached to the x in here, then we could use log rules to move that out to the front. But this log is attached to the whole logarithm, not the x inside. That's why I put the parentheses here. So we can't just bring this to the front here because it's already outside of the logarithm. It's not attached to the x inside. Right now we have something with a variable raised to something with a variable. So we're going to use logarithmic differentiation. I'm going to take log of these logs here. Okay, now we need to pay close attention here. We're going to really push our log rules to the limit here. This log is a power inside of this log we just got. That means we can use log rules with this, and we can pull it out to the front. So this ln of x comes out here, and it's multiplied by ln of x, because this ln no longer has its log as a power. It came out to the front. All right, now we're ready to do the derivative here. So if I do the derivative of everything, well, we know the derivative of ln of something is f prime, the derivative, divided by the function itself. Now, in order to do the derivative of this, I have ln of x times ln of x. I need to use the product rule because of this multiplication. So I'm going to do the derivative of log, which is 1 over x. I'll leave the log of log alone. Then I'll leave the log out front alone. Oh, sorry, this should be a plus. Then I'll leave the log out front alone and do the derivative of this. Now, in order to do the derivative of this here, I have a log plugged into a log. So I need to use the chain rule. So the chain rule says, for my first log, that the derivative of ln is 1 over whatever's inside. is ln of x. So I took care of this piece. Now I need to multiply by the derivative of my inside, but the derivative of log is 1 over x right here. And there we go. So that's it for this. Now, these actually cancel out to make things a bit simpler, which is good. And then I multiply both sides by f of x. So it turns out that f prime of x is going to be ln of x to the ln of x times all of this. Now, these both have a 1 over x in them. I'll move that here. I have ln of x, and then I took the 1 over x out of here. That's just plus 1. Okay, so the derivative of ln of x to the ln of x, which I needed to know from back here, is this. So I can simply stick this in. And while I'm doing that, I'm going to multiply these together because of exponent rules. This is ln of x raised to the 2 ln of x. And then we multiply this by what we found here. This is times ln of x to the ln of x, ln of x plus 1 divided by x. And there we go. Our derivative is really nasty looking, but that's what it ends up being for this problem. So this goes to show you that even though it may be a bit difficult and confusing, especially if there's a lot of the same type of function here, we can now differentiate pretty much any function we want or any function we can make up that we've seen in high school. Now, there are some pretty bizarre functions out there, some of which don't have derivatives anywhere, which we can't do the derivatives of those. But for most combinations of functions we've seen in high school, we can now take the derivative of them, which is very nice. All right, I will see you guys in the next video where we will start. Well, we're going to look at one more type of differentiation, which doesn't quite have to do with this. Then we're going to start looking at some applications. So I'll see you guys then.